hopefully you've seen through the concepts that we've covered so far that there are a few different representations that we can use, whether that's equations or just an explanation in words, or if it's a graphical representation. For this video we're going to have a look at some graphs that relate to work and energy. You can see that the first one that we're going to deal with is a force displacement graph. So basically a force displacement graph is just like I said, a graphical representation of the scenario where we would have a force that we would graph on the vertical axis, and the force would be represented by the vector F, and the units of measurement would be newtons, and the displacement on the horizontal axis. So basically we're looking at how much force is needed in order to displace an object by a certain distance. Generally speaking, the easiest way to look at this scenario is to first of all just consider a situation where the force is constant. So in that case the force would, the graph would just be a horizontal line. Now it doesn't seem like that's a particularly important graph, but there's something about this graph that's really important, and we've seen this idea already, but want to just come back to it again here. So when you're graphing this idea of force versus displacement, it's not so much the graph itself or the line that's interesting, it's the area under that line, or the area under the curve. So the area under the curve is going to be another quantity that we can actually relate to. And that area under the curve represents the work done or energy gained, and we're going to make the assumption here as well is we're assuming that the force is acting in the direction that the of the displacement, so that everything is in the same direction there. So that means then if we were to look at say at a displacement out here somewhere, then we can multiply the force and the displacement as we would do for the equation for work to find that area under the curve. So that actually represents the work W. Makes sense in a graphical situation, because if we've got a force, we're multiplying it by a displacement in a graph, that physically represents the area of that graph. So useful graph to consider when dealing with energy. Like I say, this sort of situation is probably not where it's most useful. It's just that's the easiest way to explain how a force versus displacement graph is useful. Another situation where it's a little bit easier to identify what's happening is something like extending a spring. Now if you think about a spring, the further you stretch it, the harder it is to stretch. So in that case, our force versus displacement graph is not just going to be a straight line or a horizontal line, it's going to be a line that has a slope associated with it. So it would look something like this. Just make sure I label my axes, just a good practice to get into to make sure it's full and detailed. And so in this situation we would see a graph that looks something like that, where that should be a straight line, a little bit wobbly with my pen. And so we can figure out then that in this situation, if we're extending the spring to this distance, then the work that we would be doing is given by that area, which in this case is actually a triangle. So here the work would be equal to half of the base, so half of the displacement S multiplied by the force. So we can just write that as half F times S in this situation because it's a spring. And so let's say the force that we applied was 5 newtons, so this value across here, if that was 5 newtons, and this distance across the bottom was say 0.1, then the force would be, the equation there would be half times 5.0 times 0.1, which would give us a total of 0.25 joules. So note there, it's just literally calculating the area of a triangle. This equation is not particularly important to note here. It's just for this scenario where we can see the change of the force over the displacement. It might be that you've got a scenario where for the force versus displacement, you might see that as the displacement increases, the force eventually levels off, in which case you could then break that up into two regions and find the area of a triangle and the area of a rectangle. So in the end, we're just looking for the area, and just doing it geometrically, so looking at the shapes that are involved in those situations. Now, the second type of graph we're going to look at is an energy time graph. And two aspects here that are useful to consider. The first that we'll look at ties into the idea of conservation of energy. So basically, for an energy time graph, we're just going to represent the change in energy that occurs over time, keeping in mind that energy and work are effectively the same thing. It's just the perspective that you're looking at. So energy, we'll use the letter E for energy here, measured in joules, and on the horizontal axis we'll have time t in seconds. Now, if we think about, say, an object that's falling, we might be interested in just looking at the gravitational potential energy, in which case what we would expect to see is that as it falls, it speeds up and eventually hits the ground below it. So that would represent our gravitational potential energy, EP. So there's just a graph of the potential energy as it decreases. The other thing that's useful here, though, is that we know that as the potential energy decreases, the kinetic energy increases. So that means that what we should see is a similar graph, but has a sort of an opposite trend that's increasing over time. So that would then represent our kinetic energy. And we know then that the total, so if we were to go through and consider the total energy over time, would be represented by that dashed yellow line. We know that that total energy is going to be the sum of the kinetic energy and the potential energy. If we had any energy losses, then that total, well, it'd still be horizontal, but what we'd expect to see is the, say, the kinetic energy might be a little bit lower, and the difference between the total and the sum of EP and EK could then be the energy losses in the form of heat and sound. So the first aspect there is that energy conversions can be represented on an energy time graph. The second aspect that we're going to quickly talk about is taking that idea of how quickly the energy is changing over time. And again, rather than sort of talk specifically, I'm going to go with an example. In this case, we'll look at, say, an elevator over time. So this elevator is going to be moving up and down and changing its height as people are getting into and out of. And so again, we'll look at the energy on the vertical axis. In this case, we're going to look specifically at the potential energy. So we're not looking so much at the energy conversions, we're just looking at the potential energy and the time over which that's occurring. So you might see a graph that looks something like this. So initially it might be on the ground floor, and so it starts at 0, and then over time it increases to a higher floor, so the potential energy increases, moving at a constant rate as it increases. So you can see the energy is increasing there in a linear fashion. Might then stay at that floor for a while, then comes back down to a lower floor, stays at that floor for a while. So in that case we can see the change in energy over time, but more specifically what we're interested in here is not just the change in energy, it's the slope of the graph itself. So the slope of an energy time graph is another quantity that's useful. So generally speaking, with graphs, we're interested in either the area under the curve, or we're interested in the slope. So in the force displacement graph, we're interested in the area. In the energy time graph, we're now a little bit more interested in the slope. So the slope of an energy time graph shows us the rate at which work is being done, so it shows us either the rate at which work is done or the rate at which energy is used. Now both of those ideas lead us to another property that is known as power. Now, power is not a concept that we need to go into in lots of detail here, but just mentioning it because it is an important one to consider in this sort of context. We can consider then that power is the work done over time. And if you look at the energy versus time graph, you can see the work being the change in the vertical axis, time being the change in the horizontal. So work over time here, we're really finding the gradient of that line. Just as an aside, or just to sort of mention this here, the units of work are watts, and 1 watt being equal to 1 joule per second. As I said though, power is not something that you'll be examined on in terms of knowledge. It's more just something else that you can, some other information that you can glean from an energy time graph.